For my Recommender Systems coursework, I have made a movie recommender system with the aim of providing useful, personalized new movie recommendations to users. So this means movies that they have not seen before. I was particularly drawn to the Movie Lens dataset for this project, which is illustrated diagrammatically below, due to the links table, as this allows for the dataset to be extended with additional content features from external sources. In fact, this is precisely what I did in my project, and I extended the dataset to include the synopsis for each movie, which ended up being a core focus of my investigation. The external dataset I used for this was selected after conducting detailed experimental analysis on 5 different datasets scraped from IMDb, TMDb, and Wikipedia. The selected dataset was then combined with the Movie Lens dataset, and data cleaning was performed, such as deduplication, dropping missing information, etc., prior to taking a representative sample, as this ensures a clean sample. 2,000 non-overlapping users were randomly selected, with 50 randomly selected temporally contiguous ratings each. These users had collectively rated 7,026 unique movies. As for the recommender systems method, the nature of my application lends itself well to content-based filtering and collaborative filtering. In particular, content-based filtering can be used to leverage the synopsis content features I gathered. However, it can lead to over-specialization. Collaborative filtering is more robust to this and can capture relationships beyond those provided by content features, but is inherently biased towards more popular items. A hybrid combination of both of these was therefore selected in order to alleviate these issues while inheriting their benefits. LightFM is a popular Python package which boasts a convenient way of implementing such a hybrid system, as it handles most of the implementation details. It is less flexible, however, and after some initial experimental analysis, I ended up discarding this method. I instead implemented the system myself, which gave me full control over the implementation details. For the user profile, reference 18 proposes an interesting method of explicitly modeling the user's knowledge of items, but is more complex and makes more assumptions than simply taking the average of item vectors weighted by the user's ratings, which is widely respected as a simple and reliable method. For the distance metric, cosine distance was selected as it does not require normalization, unlike Euclidean distance, nor does it require linearity assumptions, unlike Pearson's correlation. And for the hybrid scheme, as cascade hybrid schemes may result in biases accumulating, a weighted hybrid scheme was selected, also because the weight parameter may be flexibly tuned to our use case. As for the item representation, a fixed-length synopsis content embedding is used to represent each movie. The feature extraction method employed to compute these is the crux of my investigation. TF-IDF embeddings are used for the baseline system, but transformer embeddings, computed using a large language model, are used for the advanced system, as this has been shown to be state-of-the-art in such tasks. For example, the 2 synopses shown are highly similar in meaning because they are in fact synopses of the same show, just from 2 different sources, IMDb and TMDb. However, the cosine distance between their TF-IDF embeddings has a relatively high value of 0.81, as they do not share many common words. With the transformer method, however, the distance is 0.62 and is lower as desired. In fact, due to my previously described exploratory analysis of different synopsis databases, I was able to construct a clean dataset of 11,000 movies with their corresponding synopses from both IMDb and TMDb. Driven by the fact that corresponding synopses should be, on average, more semantically similar, and thus have a distance closer to 0, than random synopses, an observation that was loosely inspired by BPR, I conducted a detailed experimental analysis of how well the transformer method can capture semantic relationships compared to TF-IDF. Using mean absolute error as a summary metric for this, and as evident from the graphs on the right, transformer models were confirmed to indeed be significantly superior. The specific large language model to be used, however, was determined by experimentally comparing 14 different models using this process and selecting the best performing one. As seen in the figure, however, all of these models were superior to TF-IDF in any case. Okay, let's say we want to recommend movies to this user index 596. First, we must set up the user interaction matrix, in this case just one row, because there's only one user for this user, okay? And this is displayed in a bit more detail here with the actual titles of what this user has rated. But in any case, once we have set up some of these prerequisites, we're using method index 1, which is the transformer method. And there we go. These are the output scores of the CBF component. Now for the collaborative filtering component. There we go. And now to combine them, There we go. To evaluate the accuracy of the system, a ranking metric is more appropriate than a rating metric, as the final output is ultimately a ranked list, for which the relative order is more important to the user than the scores of each item. A utility-based metric is used because purely correlation-based metrics do not explicitly prioritize the top of a list. And NDCG was chosen over the shown alternatives because the utility decays slower, which better models our use case, as studies have shown that users of movie recommender systems tend to view a relatively large number of recommendations before deciding on a movie to watch. Cross-validation is performed as hyperparameters are optimized using the dataset, and it makes sense to evaluate how well they generalize to out-of-sample users. The holdout method is used for this as a less compute-intensive estimation of more exhaustive methods. As for the procedure itself, as mentioned in further detail on the slides, for each user, using only the first 80% of their interactions, we compute the ranks for the concealed movies alongside a large number of other random unrated movies, which are assumed to be non-relevant, and compute NDCG using the ground truth ranks. Some sources do not incorporate random other movies, but this is not realistic because in a real-world system, recommendation candidates cannot be narrowed in this way, as we do not know the movies that the user will watch next. A large number of random movies is used as a computationally cheaper approximation of using the entire movie library as candidates. As you can see here, these are the results of this evaluation. Here it is in table form and as a graph. In any case, the key takeaway is that the advanced method is significantly better than the baseline method in terms of accuracy. Also, the values are not significantly different for out-of-sample users, indicating good generalizability. As mentioned previously, recommending movies that the user has not seen before is one of the aims of this project, and this is justified by the observation that people rewatch movies less often than in other domains such as music. It is also further justified by a number of studies which have shown that in general, improving novelty improves user satisfaction in real-world systems and also addresses over-specialization. To measure this aspect, the shown formulation of novelty is used in line with references 59 and 60 instead of alternatives due to its simplicity and driven by the estimation that users who interact with a rare item are likely to know similar other rare items. As you can see, I am using the novelty formula in the code here, and if we run it, these are the results that we get. From the graph, we can see that novelty is actually significantly worse with the advanced method in comparison to the baseline method. So in summary, although ranking accuracy is significantly improved when using the advanced transformer method compared to the baseline TF-IDF method, novelty is significantly worse, displaying signs of the well-studied novelty-accuracy trade-off dilemma. A comparison with the random method highlights that optimizing solely for novelty is also undesirable, however. But without a better understanding of the precise novelty-accuracy trade-off that users in this particular domain prefer, there is insufficient evidence to definitively claim that the advanced transformer method is better than the baseline TF-IDF method in meeting the original aims. To this end, online experiments and further comparison with popularity-based baselines, such as simply recommending the top K most popular items, would be beneficial. Ablative experiments provided strong evidence that the transformer method itself is sound, however, so further study into other aspects of the system, in particular the weight hyperparameter given to the collaborative filtering component, has strong potential for mitigating this issue. Okay, so for the system demo, the command to start up the UI is python regsys-ui.py with a M flag set to 0 for the baseline system or 1 for the advanced system. As soon as we run this command, we have this sign-in screen. Let's try user index 596, and we are immediately presented with our recommendations, which we can go through, and we can go past the original 20 if we would like. But in any case, whenever we change what we have selected, this section on the right here automatically dynamically updates to provide us with additional information, and including the synopsis, which we can interact with very conveniently, just like so. For the advanced system now, it's actually the same command, just with a 1 there, and everything actually looks exactly the same. We can actually even use our cursor instead of the keyboard, by the way, so whichever is more intuitive for the user. But in any case, it looks exactly the same. The only difference is that the recommendations themselves are powered by the advanced system this time. And also a really cool thing about this user interface is that it is fully responsive, so it looks great on many different screen sizes. As you saw in the demo, only one item is shown in detail at a time, although a less detailed list of 20 items is also shown. In line with reference 49, this allows the user to process information without being overwhelmed, while also giving them a sufficient level of autonomy and choice. In fact, careful consideration was given to all aspects of the user interface, a key one being the following of Gestalt principles, such as the principle of closure, which is illustrated here. And that's it for the presentation. Thank you so much for your time.